Okay, so let's get started. Okay, so I got the YouTube rolling, so everything is okay. So remember here that last week I say that I still owe you one example for 5.5. 5.5 is okay. Power theory solution. Okay, near. Remember here, near is very important. Or around. Our textbook said that around. Some other textbooks say near, around. Singular point, regular singular point, regular. Point. X equal to 0, regular here. Okay. So of course that there is also a method of finding out what they call irregular singular point, but we don't have any time, so we just have to be very happy with just only regular single point. And then as you can recall, that the method we are using is what we call Frobenius method. Okay. Now, so let me give you a second example, and this example is actually a little bit shorter than the one we talked about last Thursday. Okay. First of all here, well, let's go ahead. So let's talk about, well, the DE itself. The DE here is going to be 3xy double prime plus y single prime minus y equal to 0. Right. Okay. And then, well, and then the center here says x sub 0 equal to 0. Am I correct? Right. Okay. Now, so let me just to convince you once for all. I mean, first of all, I should say that x equal to 0 is what they call regular singular point. Okay. First of all, here I need to convert this one here into a format in which that this one here has a coefficient of 1. So in that case, I have to divide left-hand side, right-hand side by 3x. Am I correct? Yes. Okay. So I got here, well, so I got here y prime double prime plus 1 over 3x y single prime minus 1 over 3x y equal to 0. Am I correct? Yes. Make sense or not? Okay. And then after that here, well, first of all here, I need to do two limit. The first one is that, well, so I got here limit. Well, hang on a second. I think that I have just only limited space. I'm going to write it down here. So I got here, well, y double prime plus 1 over 3x y single prime minus 1 over 3x no prime equal to 0. Right? Okay. So this one here is what we call px qx divided by px, and this one is rx divided by px. Okay. So the first limit is that, well, the limit here. Okay. And then okay, x minus 0, no square, just only linear here, as x here is approaching to 0 here, and then you have to multiply by 1 over 3x here. Well, so it goes without saying here, well, this one is going to be the same thing as limit as, well, so this one is cancelable, right? Okay, so eventually here, it goes without saying this limit here is going to be equal to 1/3, am I correct? Which is a good finite number, right? Okay, let's go ahead and set it aside. I have to go to the second limit expression, which is the limit here, x minus 0 square, and then x approaching to 0 here, and then time again, negative 1 over 3x. Well, of course, it goes without saying here. So this one becomes x squared, right? And this one becomes 3x here. And then if I plug in x equal to 0, go ahead. So it's going to be equal to 0. Am I correct? So this one is finite, and this one is finite, meaning that x equal to 0 is actually considered as a regular singular point. Am I correct? To be sure, it is a singular point, but it is a regular one. So meaning here, it is fall within the method of Frobenius. To solve it, right? Okay, and then here, according to the way that we discussed here last week here, so we got, well, so you got y here equal to sigma sum n equal to 0 infinity. Am I correct? Yes. Remember here we are talking about Frobenius. Okay. And then here, and then, well, a sub n x n plus r. Am I correct? Yes. So the only difference between this one and the one that is once again, the one that is ordinary point, which is 5.3, I believe, is that we don't have any r here. So the only thing at 5.3 is that we got only r here as far as the exponent for the x is concerned. Okay, okay, and then here, and then what?
How did you get 1/3 for the first one and 0 for the second? For limits, I learned that you initially plug in a for x and start there.
What do you mean? No, this one 3x is here, so I have to divide left hand side, right hand side by x. This is the original here, so I have to divide 3x here, left hand side, right hand side, and that is what I got. Okay, so this is the limit here. Yes or no?
That one's not 0 as well. It's 1/3.
No, because this one here, because 1/3, of course, this one here, well, so if you get rid of 0, because 0 is nothing, right? That's going to be equal to limit here, x, 3x.
0 times that expression, though, correct?
The what?
X minus 0, that becomes 0, and then 0 times that expression.
You're talking about this one? You're talking about this one?
No, the first one.
Yeah, the first one is 1/3. 1/3. 1/3, did you see it? This one here, x. So you can pretty much get rid of 0. So x canceling out 1/3, right? So if I plug in x equal to x approaching to 0, so nothing is going to be 1/3.
Okay, gotcha. Yeah, I see that now. Thank you.
Okay. Okay, and this one, of course, is negative 1 over 3x, right? Okay, it's going to be equal to 0. Negative 0 is 0. Now, and then the single prime is going to be equal to sigma sum n equal to 0, infinity, right? Okay, and then n plus r, and then a sub n x n plus r minus 1. Right, okay, that is the first prime. Okay, and then the single prime here, I had to put it down here because I'm running out of space. So I got here double prime equal to sigma sum n equal to 0. Remember here, this is one of another different here. When we were talking about ordinary point at 5.3 here, so we're talking about this one is 0 and this one should be 1, right? And this one should be 2. But here, since we are talking about n plus r, so that's why that n still 0, 0 here. Okay, and then of course that here I have to take this one and put it down here as coefficient n plus r minus 1, and then n plus r, and then a sub n, and then x here n plus r minus 2. Right? Okay. So this is no prime. This is single prime. This is double prime. Okay. And once you got everything in good order here, and then proving also that x equal to 0 for this particular dE is indeed what we call singular point, but not bad singular point. What we got is a good singular point, and we call it regular singular point. Remember here, irregular singular point, we do not touch it. Okay, okay. Hey, once we got this one here, just go ahead. It's time for us to plug in everything here. Okay, okay. So we got 3x and then single is 3x here and then double prime. Okay, so I got here, well, 3x sigma sum n equal to 0, infinity, right? N plus r, and then n plus r minus 1, a sub n, and then x n plus r minus 2, to make sure that I got it right. Yes, okay. And then plus here. Okay. Well, so this one here, I don't have anything coefficient here. Okay. So I'll have to just plug in exactly the single prime here from my right hand side. So I got here single sigma sum n equal to 0, infinity. Right. Okay. And then n plus r, and then a sub n, and then x n plus r minus 1. Okay. Yes. Everybody okay? Right. So it's just a matter of plugging in what I got here into the DE itself, right? Okay. What is the last one? The last one is no prime, which is actually the shortest one. So it's going to be equal to minus sigma sum n equal to 0, infinity, and then a sub n, and then a sub n here, and then x n plus r equal to 0, right? Okay. Now, let's go back into the DE here. I just want to give you a casual observation here. Did you see it? So this one here, well, so I got, I mean, as far as the second coefficient is concerned, this one is constant and this one is constant. But if you look at the first coefficient here, this one is non-constant. So that if you try to solve it using characteristic equation, no, this one is off. I think so. I think as far as our knowledge is concerned, our toolbox is concerned, toolkit is concerned here, well, power theory is the only way to solve this one, right? I don't think there's any other way to solve this one here. Okay. Now, so let's talk about, well, so well, okay, it's gonna be minus sigma sum n equal to 0, infinity here. Okay, a sub n, and then x n plus r equal to 0. So let's talk about, well, so I'm going to assign this one here as a, right? And I'm going to assign this one as a b, and this one here as a c here. Okay, so this one is c, right? Okay, and this one here is a, b, c. Okay, and then I have to break it down because it's too much. Okay. So I'm going to assign this space here as a, and this space as b, and this one as a c here. Okay, so let's see what happens. Well, first of all here, so let's make a shortcut here. If I take this one and put it in here, okay, so this one here, x is a linear, right? So of course it has the effect of reducing -2 become -1 only. Am I correct? Right? So we have to put the 3 outside here. Okay, so I got here, well, so this one is a here. So it's gonna be sigma sum n equal to 0, infinity, and then 3, and then n plus r, and then n plus r minus 1, a sub n, and then x n plus r minus 1. Yes, so I'm making a shortcut. I'm no longer talking about before I canceling out -1 into -2 into -1, right? So this is a here. Okay, excellent. Okay. Okay, so let's put it aside. I don't want to do anything because I would like to make comparison before I make my move, right? Okay. Okay, so this one here is the space for B here. So the B here is going to be this one. Yeah, this may sigma sum n equal to 0, infinity here, n plus r, and then a sub n, x n plus r minus 1. Okay, so if you make a comparison between the first A and the second B here, so look like something they have common is that n plus r minus 1. Am I correct? Yes. Okay. But first of all here, well, do not make any judgment yet because we have to do something else. Okay. Okay, and then so let's talk about the C here. So the C is going to be here. Okay, the C here is going to be, well, negative sigma sum, and well, so let's talk about the negative. I'm going to put the negative later on. So eventually I have to reconcile here A plus B minus C equal to 0. Did you see it? I put the negative here. Okay, do not forget at the last minute that when you put in A, B, C together, so this one is negative. Okay, so sigma sum n equal to 0. Okay, and then infinity, right? Okay, and then A sub n x n plus r. That's it. Okay. Okay, first of all here, let's focus on n plus r. Okay. Uh, okay, so let's do this one. If I, first of all, of course, that according to the standard procedure here, first of all, we need to focus to make sure that all the exponent to the x is going to uniform. Am I correct? Right? So this one is n plus r, and this one is n plus r minus 1, and this one also the same thing, just like b n plus r minus 1. Well, of course, here the first tendency is that this guy is a minority. Am I correct? Whereas x n plus r minus 1 is the majority. Am I correct? Yes or no? Right? So my first tendency is, of course, that I would like to convert this one here into x having the exponent n plus r minus 1. Am I correct? Yes, because that is going to be the least resistant, the least work. Right? Okay, let's see what happened here. I don't guarantee, I'm not going to guarantee that that one work, but at least that I have to give it a shot. Okay, so it's going to be here. Remember here, that if I am subtracting any n here by 1 here on this, the first term and the second term, so meaning here as far as the sigma sum is concerned here, I do have to do the other way around, which is that I have to plus 1. Am I correct? Yes. Minus 1, plus 1. Yes. Okay. So it's going to be equal to sigma sum and, okay, equal to something, something here, and then a n minus 1. Am I correct? Remember here we have to subtract everything by 1 here, right? As far as the term is concerned, whether the n is actually the sub number or the n is the power, the exponent here, regardless, well, so we have to subtract by 1, and then x n plus r minus 1. Everybody okay? Right? So meaning here, if I subtract 1 from here, subtract 1 from here, so it's going to be plus 1 here. Okay? Yes. So as far as the, see, this is what they call shifting. Okay. Everybody okay? Shifting. Now, and then after that here, well, first of all here, I don't want to guarantee yet. Okay, so this one is work. But that is at least that is my first experiment. That is my first move here. Now, so do you think it's possible for me, while keeping the exponent to the x here, n plus r minus 1, and b also the same thing, do you think it's possible to convert the n number, the sigma sum, the starting n number from 0 into 1? Yes, it is quite possible, because all we have to do is what we call shading. Am I correct? Yes, right? Yeah. So remember here, from here to here is what we call shifting. Am I correct? Right? So the next move is that I need to do what we call shading, meaning what? Instead of starting from 0 here, so I'm going to start from 1. So in that case here, I'm to shade one of the term outside of the sigma sum. So in this case, so this one can be the same thing as, okay, it's going to be, well, it's going to be 0 plus r, and then a sub 0, and then x, and then x here, and then what? And then 0 plus r minus 1. Am I correct? Right? Okay. Am I correct? Because I am shading n equal to 0, because I would like to start n equal to 1 in order to be consistent with the C here. Okay. So, uh, it's going to be plus here, sigma sum n equal to 1, right? Because the 0 is already shaded into just one individual term, right? Okay, and then n plus r infinity a sub n and then x n plus r minus 1, right? Okay, so this one here become, well, let me do some housekeeping here. So I got r and then a sub 0 and then x r minus 1. Am I correct? Right. Okay, and then plus, okay, and then sigma sum, still the same thing. All I have to do is just copy from the top to the bottom, n equal to 1 infinity n plus r and then a sub n x n plus r minus 1. I'm done. Okay, so look like as far as B and C is concerned, I'm good, because, well, as far as the starting n is concerned for sigma sum, from the B and C are the same thing, uniform. They are uniform, and also likewise as far as the power to the x is concerned, n plus r minus 1, and for the C here I got also the same exponent. So far so good. Am I correct? Okay, now I'm turning my attention to the C here. C here, I need to follow whatever I did on the B here, on the A, sorry, A, sorry. Okay. So in that case here, so what I'm going to do is that it's going to be the same thing as shading again. Okay. So I got here, well, I got 3 and then 0 plus R and then 0 plus R minus 1. Right. Okay. 0, 0. And then a sub 0 x 0 plus r minus 1, right? Okay, and then once I already shared one of the term, so I have to continue with the sigma sum as usual. Sigma sum n equal to 1. Did you see it? 1 here. And then infinity 3 n plus r n plus r minus a minus 1, sorry. Okay, and then, well, so I don't have any space here. Well, that's okay. Uh, a sub n, and then what? Well, a sub n here, and then x here, n plus r minus 1. Right. This is 0, this is 1. Okay, so let's do some housekeeping here on the one that, the first term that we shared. Okay, so I got here, well, it's going to be 3r. So this one is nothing, 3r, right? Okay, and then r minus 1, a sub 0, and then x r minus 1. Did you see it? So this one is 0, nothing. We can get rid of it. Yes. Okay, and then plus again here, sigma sum n equal to 1 infinity. So I do not have to change anything. All I have to just copy exactly like the one on the previous line. So I got 3 here, n plus r, and then n plus r minus 1. Okay, and then a sub n x n plus r minus 1. Right. Okay. I think so far so good here. Okay, but first of all here, I need to label them. Right. I need to label them one by one. So this one here, I got here, well, to be consistent, again, it is just only my invention. So it's not necessarily the textbook is going to be saying the same thing. Okay, so I'm going to assign this one is a A1, right? And this one here, the one with the sigma sum, I'm going to assign it as A2. Yes, A1, A2. Right. So likewise, I'm going to follow the same labeling here. So this one I'm going to label as B1, and this one here I'm going to label as B2. Okay, but as far as C is concerned, I don't have to relabel them again. So this one is exactly like the way it did, which is C only. Okay. Right. Okay. Okay, so first of all here, I need to combine, remember here, just like the way we did last week here, I need to combine with an A1. Well, so this one I have to revise just a little bit here. So I have to do here A1 plus A2. Am I correct? Yes. Is that or not? Because I break it down A here into A1, A2, right? And then plus B1 plus B2. Am I correct? Yes or no? Right. Okay. And then here, well, the C here. Remember here, the C here has to be subtracted, right? Okay. Do not forget. So it can be minus C equal to 0, right? Okay. And of course, from here, I can say that, well, so I'm going to say that, well, A1 here plus B1, I'm combining the 1, 1 together here, and plus B, excuse me, plus A2 plus B2 minus C equal to 0. Okay. Right. Okay. So this one got sigma sum, and this one got sigma sum, and this one got sigma sum. And the good thing about all of those three sigma sum is that all of them has already converted into something that is uniform, not only in terms of the power of the x, right, but also the starting point for the sigma sum. So you can combine A2, B2 minus C together in just one sigma sum. Right? Yes, right. Okay. Now, so let's deal with this one here. A1 and B2, A1 and B1 here has to be equal to 0 in order to be uniform, and in order to be that the equal sign, left hand side, right hand side, 0, 0, 0. Right. Okay. In order to be consistent with the meaning of in order to be consistent with the meaning of the equal sign. Right. So remember here that I told you in an informal language that equal sign equality or equal sign is actually the soul and power of algebra, right? Okay, so if you put an equal sign left hand side, right hand side, you have to be consistent if you have to go to the gate of hell. Yes, I'm serious. You have to be consistent, even if you have to go to the gate of hell. So you have to be consistent, equal, equal. Okay. So here in this space, I'm to do A1 plus B1 equal to 0. Okay. So let's see what happened here. Okay. So A1 is this one. So A1 here is give me the 3R and then R minus 1, A sub 0, and then X and minus 1. Am I correct? So this is exactly what the A1 say. Right? Okay. Can everybody follow me? Am I talking too fast or not? Okay. And then B1 is this one. B1 here is going to be plus R A sub 0 X and minus 1. This one has to be equal to 0, right? So this one here is what I call A1, and this one here is I call A2. Okay. Right. So this go to here. Everybody okay? Right. Everybody following, I mean everybody able to accept the logic of that this one got to be 0, this one got to be 0 in order for the equal sign to be effective, to be what it has what it meant to be, right? Okay. So, well, sorry. I'm sorry. This one should be B1. Sorry, I'm sorry. I got it wrong. Sorry. Yes. And then just by looking at this one here, so look like here that, well, I can easily observe that A sub 0, I got it from the first term, and the A sub 0, I got also from the first term. Okay, that is one. Okay, that is one information here. The second information I got here is that, well, x raised to the power n minus 1, I got it from the first term, and also I got it also the same x on the second term. So meaning here, we can go without saying here, since the right-hand side of 0 here, so I can canceling this one out, canceling this one out. Am I correct? Right, okay. So eventually here, the only thing left is going to be 3r, this one here, which is containing r, and then this one here. Everyone okay? Right, so it's going to be here 3r and then r minus 1 plus r equal to 0. Right, okay. And then here, and then of course here, so look like here, okay, let's see what happened. So I got here, well, 3r squared minus 3 3r plus r equal to 0. Well, so let me ask you an algebra question. This one is very simple. Well, if you look at this one here, do you think that I can just go ahead canceling out r here because I got r on the first term and I got also 1r on the second term? Can I grant, it just happened that you are looking up here, can I just canceling out divided the left hand side right hand by r? Grant, do you think that that is an advisable move or not, Grant? What do you think? Why? Why?
I think I'm following along okay. It's kind of hard to see down there because of all the camera things, but it looks like, I mean, you could. I already multiplied mine out in the steps ahead, which is why mine's kind of looking at it. But when I look at it now, I guess you could, and it would make the math a lot easier, because then you would just get 3r minus 2 equals 0, correct?
The answer is no, Grant. You are, I mean, meaning that if, I mean, logically that you are correct, that you can go ahead canceling out r here, but in the end here you are missing one of the root because you are missing r equal to 0 as one of the root. Did you see it? Makes sense. So this is that is actually another cardinal rule in algebra, college algebra. Do not ever try to simplify by canceling out one of the variable left hand side, right hand side, because you are going to miss one of the root. Yes, make sense or not? Okay, so be very careful. Be very careful here. Okay. Yes, everybody okay? Right. Be very careful. Okay, so we just have to just go ahead and do the traditional way here. Okay. So I got here, well, 3r squared minus 2r equal to 0. Yes, right. So now here, well, I can pull out r here from the first term and the second term. So I got here, I got r and then 3r minus 2 equal to 0. Am I correct? Yes, right. So meaning what? How many r we got? How many r? We got 2r. Am I correct? That is very consistent because we are talking about quadratic, right? Remember? Right? And the cube, we can expect you got 3r. Right, okay, and then here we got square, meaning that we got quadratic, meaning that we expect to see 2r, right? So what is the first one? The first one is r equal to 0, right? And what is the second one? The second one is r equal to 2/3. Did you see it? Can you see it down here? Lucia, can you see it? No, you cannot see it? I'm sorry. No, I'm talking.
If you go to view at the top left options, you click that, then you click full screen, it will allow you to see that.
Okay. Can you do it, Lucia? Full screen? Okay. So, okay then. Well, I'm sorry. It's kind of, I'm sorry here. So this one is up and down here. So I got r equal to 0 and then r here equal to 3 seconds. Right. Okay. Well, this is what we call indicial root indicial. So this is what we call indicial root. Indicial. So do not get confused with insidial. Insidial is incident, am I correct? But indicial, index, something to do with index, but it's called indicial roots. Indicial root. Okay. Right. Okay.
Professor,
Mm-hmm.
would that be 2/3?
Yes, that's correct. You are correct. That's correct. 2/3. I got mixed up. But okay. So that is what they call indicial root for some reason. But again, here just follow the logic of the textbook here. I don't have any. I don't have. My position is, well, I just carry out what the textbook say. Okay, indicial root. Okay, that's it. Now I'm done here as far as the B1 and then A1 is concerned. Let's talk about the second square bracket here. So I got A2 plus B2 minus C here equal to 0. Okay, like I said before here, that A2, B2, C here, we already working very hard. We already work very hard so that at the end of the day, when I find out all of them, the A2, B2, as well as C here, they are all having the same sigma sum with the uniform starting end as well as the power of x. Am I correct? Yes. Okay. So in that case, since I have only small space to complete all of them, so I'm going to just make a shortcut saying that, well, so this one is going to be equal to sigma sum n equal to 1 infinity. Okay. Right. Okay, and then, so let's start with this one first. Well, I'm not so sure I have a space here. Can I just erase this one here because this one is no longer in use? Everybody okay? Can I erase it? Okay, so I'm not so sure I have enough space. Okay, so let's see what happened here. Okay. Oh, so I got here, well, A2 plus B2 minus C here equal to 0. Okay, so let's talk about the A2 first. A2 here, we got, well, I'm going to combine sigma sum n equal to 1 infinity here. So I got 3n plus r, and then n plus r minus 1, and then a sub n, and then x n plus r minus 1. Right. So this one is what they call A2. Right. Okay. So let's go forward with the B2 here. So the B2 here, well, okay. So I'm too lazy to write down sigma sum again, okay, because of the limitation of my space here. So I just writing down the term here, okay, without having to write again for one more time the sigma sum, okay. Okay, so it's going to be plus here, okay, angle bracket. I got here n plus r, and then a sub n x n plus r minus 1. Okay, so this one is what they call B2. Okay. Yes. Okay. And then after that here, well, there's only one term left with the C. So keep in mind C is negative. So make sure that it has to be negative. Negative here, sigma sum, and then A. Okay. And then n minus 1, and then x n plus r minus 1 equal to big fat 0. So this one is what they call C here. Right. Okay. Okay. Now, and then after that here, what you get? And then after that here, so remember here, this is supposed to be 0. If you have the left-hand side, the right hand has to be 0 in order to be true to the real meaning of equal sign here. So everything has to be 0. This one has to be 0. This one has to be 0. This one, the sum of this one minus this one has to be 0. Am I correct? Left-hand side 0, right-hand side 0. Am I correct? Right? At the same time, at the same time here, So I look like here that the first term we got x n plus r minus 1, the power. The second term also have the same term, which is x, and then raised to the power of n plus r minus 1. The third one also the same thing. Can I just divide it left-hand side, right-hand side? Am I correct? Yes or no? Makes sense? Right? So remember here, this case is different from the one that I tap you about the r here, because here I'm not looking for the root of x, but here I'm looking for the root of r. Am I correct? Yes. So it is safe to canceling out, to take out x raised to the power n plus r minus 1 from the first and second and third one. Yes, because I am not looking for the solution or the zero in terms of x. But here I am looking for root in terms of r. So you are not supposed to canceling out. But here I'm okay. Yes, makes sense or not? Right? Okay. So, and then eventually here, well, if you allow me to say that, well, a plus b minus c equal to 0, so it's going to be equal to 3n plus r, and then n plus r minus 1. Okay, a sub n, this one is no longer in use because I already canceling out. I already take out and divide the left hand side, right hand side, and then plus n plus r, and then a sub n. Okay, and then minus, remember here the c is minus here, right? Okay, a n minus 1 equal to 0. Yes. Raise your hand if you still confused how to follow from this line into the next line, please. It should be, if you follow through with the first example and then the ordinary point here, it should, I mean, it shouldn't come as a surprise. Yes, makes sense? Okay. And then after that here, well, so look like here, well, I got initial root from A1 plus A plus B1. But here, what I'm aiming for is getting a recursive relation or recurrent relation. Right? Okay. Okay. Remember here, when we are trying to figure out a recurrent relation here, so the one that has bigger sub n number should be on the left hand side. Okay, the one that is less has to be on the right hand side. Okay, so meaning here, well, you have to make sure that your father was born before you. Do not turn it around. Do not mix up by turning it around. Okay. Okay. So meaning here, well, if you're talking about this is n, and this is n, and this one is n minus 1. So look like here, this and this have a higher sub number. Am I correct? Right. So in this case, so look like this one has to be tossed to the right hand side because here the n minus 1 has a less number. Okay. Okay. And then of course here it's going to be here a sub n. Okay, 3 n plus r, and then n plus r minus 1. Right. Okay. Plus n plus r. Right. Okay. Equal to a n minus 1. Right. Yes. So we are close into getting a what we call a recurrent relation. It's going to be equal to a sub n equal to a sub n minus 1 divided by 3n plus r. Okay, and then n plus r minus 1 plus n plus r. Right. Okay, so this is what we call recurrent relation. But of course here, so look like here, I can simplify the denominator here, okay, because I got n plus r and then n plus r. So it's going to be equal to a n minus 1 and then n plus r, and then so I got here 3n plus 3r minus 3 plus 1. Okay, a n minus 1 divided by n plus r, and then 3n plus 3r minus 2. So that is what they call the recursive relation or recurrent relation. Yeah, that's correct. That's correct. Okay. Yes. So this one is correct here. This one is the correct. This one is the correct solution. So this is what they call a recurrent relation, right? Okay. Just for your side knowledge, how do you go from here if you have to go forward? Well, first of all, here we got how many R we got? So we got 2R. Am I correct? Yes. Okay. So in that case here, so we have to do two analysis side by side, if you will. First of all, here you need to plug in R equal to 0. So R equal to 0, this one becomes 0, this one becomes 0. Am I correct? And then after that, you got, well, what is the A1, A2, so on and so forth, long, very, very, very long, just like the way that we did here when we were discussing the ordinary point, 3.3, I believe, 3.3, right? And after we finish with the R equal to 0, so let's go ahead do the second one, which is R equal to 2/3. And then we have to do one more time here. So it's very, very long, very, very long. Okay. So we have to do the first R and the second R. Now, what happened here? If we got 3R, we have to do the same thing. The first R, the second R, 3R. Very, very long, very, very tedious. So I don't think that it is appropriate to give you in the class, but you got the idea. Right. Okay, makes sense. Okay, so that's enough for the 5.5, the power series solution around the regular single point using what we call Frobenius. Okay, so let's take a break first, and then after that, we are going to talk about the next section. The next section here, well, as far as the calculation is concerned, it's not very much. It's not very much, but we are going to use quite a lot the partial fraction. So hopefully, I can finish the next section by today. Okay, and then we're going to talk about the last one tomorrow. And then if everything goes well, so meaning here, well, I don't have anything left to discuss here. So meaning here, I can just let you go on Wednesday so that you have more time to study. So you don't have to come here. Okay, so let's see what happens. Thank you. So let's take a break first. Okay. The what? No, I don't have any homework. Remember here, for this 5.5, the homework is too tedious. Okay, remember here, if I give you, there is a problem on the Wiley Plus, but if you give a problem here, so this is very, very unforgiving. So make a small mistake and then you're going to wrong all the way here until the beginning. So I don't want to penalize you for being actually that kind of humanly. I mean, I don't want to test your accuracy, so on and so forth, because it's my job to give you the principle, but not about testing your endurance. Okay, so I'm not going to give you any homework, but I do give you handout. Did you see it, Lucia? Right. So go ahead, practice the first one, the second one here, so on. So okay, okay. Okay, let's get started again. So I would like you to turn off your webcam because I would like to take attendance, please. Okay, Jack is here. Okay, Sam is here. Brandon is here. Lyric is here. Rachel is here. Lucia. Grant is here. Mohammed is here. Okay. Okay, now let's talk about the next one. The next one is what they call totally different from the power theory. And in fact, it has nothing to do with power theory. So this one is what they call Laplace transform. 6.1. 6.1 here is what we call Laplace. It's a French word, Laplace, like Laplace or Laplace. Transform. Okay, here. I consider it very important to tell you about why we have to learn this one. What is the whole purpose of that introducing you to this idea? Okay, so I would like to explain using a complex number. Remember here that when you talk about complex number is always in the form of a plus bi, right? Okay, so here I'm trying to explain, to give you a motivation behind why we have to learn this one. Okay, so it doesn't have anything to do with complex number, but I just want to borrow this example, to illustrate, to give you a motivation, right? So this one is a, this one is b, and then I is actually square root of 1, -1. Am I correct? Yes. Okay, and in fact here, since high school, you already learned that a here, as far as a concerned, this one is a. Am I correct? Right. So this one is what we call x. X is what we call real axis. And this one here is the y, and the y is what they call, well, it's called imaginary axis. Right, so the b is going to be here. So this one is b. Am I correct? And then if you're talking about the z equal to a plus bi, so it's going to be here, right? Okay, yes. So this is z equal to a plus bi. Am I correct? Right. So this is one of the representations of a complex number. So in terms of the axis, two axes. So the one that is horizontal is what they call real axis. This is a real number, right? And then this one here is the imaginary axis, which is whatever that is attached to the I, right? Okay. Now, so let me give you an example. So let's say that if you become an engineer, I mean, you already working as an engineer, and then that for some reason here that you are investigating a problem, and the problem here giving you a z number, which is complex number. Z here, let's say equal to, I have a note, uh, equal to square root of 3 plus 1 I here. Okay, I choose square root of 3, 1 here because I would like to make sure that the example I gave you, the illustration I gave you is as simple as possible. Okay, without, so that you do not get lost. Okay, now, so let's say that, well, so what happened here, if I have to find out what is g square? Well, g square, of course, is very simple. Okay, it's going to be square root of 3 plus 1 times I. Remember here, this one is A and this one is B, right? Okay, and then squared, right? So it's going to be equal to, okay, square root of 3 square plus 2 square root of 3 and then 1 I, right? And then plus I here square, am I correct? So it goes without saying here, square root of 3 is 3 and then plus, okay, 2 square root of 3 I, right? And then minus 1. Remember here, square root of I is actually nothing but minus 1, right? So go ahead, canceling out. It's going to be equal to 2 plus 2 square root of 3i, right? So this one is the A and this one is a B, right? Am I correct? It's very simple, very easy, right? Now, what happened here, if you have to calculate, let's say, z to the third, well, this one here is going to be a little bit involved, but again, still doable because I got here square root of 3 plus I here cube is going to be equal to, okay, it's going to be equal to 3 1/2 cube according to the formula, according to the binomial formula here, and then 3, and then square root of 3 1/2 square, and then I, and then plus 3 again, 3 1/2, and then I here square, and then plus I here cube. Am I correct? Yes. Okay. So eventually here I get here 3 raised to power 3 second plus. So this one is going to be 3 here, 9i plus, okay, 3 square root of 3 minus 1, right? Plus, okay, so this one here is going to be equal to minus I. Yes, because I cube is going to be equal to I square I. So this one is minus 1 minus I. Did you see it? Right. So eventually here, what we got is that it's going to be here 3 square root of 3, right? Plus, okay, so this one is minus 3 square root of 3, right? And then plus 9i minus I. So it's going to be equal to 0, okay, plus 8i. Did you see it? Makes sense? Okay. So, and then go on and going forward here. So let's say z equal to 4. Well, it's going to be very tedious, but still doable. Okay. And then what happened here, if you are in a situation in which that you have to find out square root of 3 plus I here to the 10. Well, so it's going to take the whole day, perhaps. Am I correct? Okay. Not only that, so let's say, well, what happened here, if you are in a calculation in which that require you to calculate, to evaluate square root of 3 plus I here 1/2. So this one also, I don't think it's possible at all. Am I correct? Yes. So in that case here, well, we have to rely on a method, what they call the Moivre theorem. Are you familiar with the Moivre theorem, or even remotely remembering the Moivre theorem? The Moivre theorem. Do you remember? Anybody still remembering remotely, even remote? You don't have to understand how does it work, but at least that from the name. So this one is actually included in precal or trigonometry. Okay, so the Moivre theorem is going to be like this here. Okay, so the Moivre theorem is that, well, so this one here, well, if okay, the Moivre theorem is actually using what they call, well, it's what they call polar, okay, complex number. Complex number. Okay. So remember here, we are still using the same example with this g here equal to square root of 3 plus I, right? So in that case here, this one is the a and the b is equal to 1. Okay. Now, so a here is actually here, am I correct? So I'm going to say that this one here is a equal to square root of 3, am I correct? Yes or no? Right? And then as far as the b is concerned, b is here, so I'll say b here equal to 1, right? Okay. And this one here is the imaginary axis, and this one here is the real axis. Real axis. Okay. And then here, and then, well, this one is the point. This one is the g here. Okay. So it's got square root of 3 plus I here. Okay. Now, and then go ahead, draw a rectangular here. Okay. So if I connect the 0, 0 into the z point here, right? So this one is b equal to 1, and this one is square root of 3. Am I correct? Right. So it goes without saying here. So this one is 30 degree. Am I correct? Yes or no? Yes or not? Yes or no? Because, well, this one here, this one is square root of 3, this one is 1, right? And in fact, you can say this one is 2. Yes. Makes sense or not? Right. So in that case here, so instead of representing z here with the square root of 3 and then 1 here, so I am choosing to represent z here in terms of what we call trigonometric expression. The same thing, but instead of looking directly at square root of 3 and I here, so I'm going to say that, well, so this one here, the b here, if you look at this one here, the b here is actually the same thing as 2 times cosine, sorry. Am I correct or not? B is actually the same thing as 2 times cosine 30 degree. Okay. So let me, for those of you who are confused, okay, so remember here, if you look at this one here, okay, so it's going to be here that sine 30 degree is going to be equal to 1 over 2. Am I correct? 1 over 2. So I would say that this one is B. Yes or no? So in that case here, so B here is going to be equal to 2 times sine 30 degree. Am I correct or not? Right. So did you see it? I'm not going to change anything except that instead of representing with square root of 3, so I am choosing the expression in terms of trigonometry. Right. So B is 2 times sine 30 degree. Everybody agree with me or not? So this is nothing but trigonometry which just belong to the pre-calculus. Right. Everybody okay? Right. And in the same token here, so I'm to represent A here with trigonometry expression. So A here, well, if you look at this one here, that cosine 30 degree here equal to A divided by square root of 3. Am I correct? Sorry. So it's going to be equal to A here divided by 2. Am I correct? Am I correct or not? Yes. A divided by 2. Am I correct? Yes. And then you multiply here. So I got here A here equal to 2 and then cosine 30 degree. Am I correct? Right. Did you see it? I didn't change anything at all except that I am expressing the A and B here in terms of trigonometry. That's it. Right. Okay. So right now that I got a new form here. So from here, from square root of 3 plus 1 times I here, I convert into, okay, I convert into 2 cosine 30 degree, right, plus 2 sine 30 degree, and then I. Am I correct? The same thing. Am I correct? Yes or no? Right? So I didn't do any changes at all. No, no, I didn't do any change, except I'm just representing here square root of 3 and 1 here into trigonometric function. That's it. And then according to the Moivre theorem here, so we got something which is actually very, very simple, very, very straightforward. It saved my day quite a lot. Because what it says is that, well, if you have, let's say, well, R, okay, cosine theta plus I R sine theta, right? Okay. And then if you raise to the power of n, okay. So this one here, according to the theorem, the Moivre theorem here, so this one is going to be equal to R n, do you remember? And then cosine n times theta plus I sine n plus theta. Did you see it? Do you still remember or not? So this is what they call the Moivre theorem, right? Okay. And then in fact, that you can do another one. Let's say that, well, we can also, let's say that, well, if you have R cosine theta plus I sine R theta here, 1 over n, I'm talking about square root here. So we have also another formula, which is R 1 over n, and then cosine, okay, theta plus 2 pi k divided by n plus I here sine theta plus 2 pi k divided by n, right? Okay, right. So I'm not going to go detail because here this is not a lecture about trigonometry. I just want to give you an illustration, the use of what we call Laplace transform. Okay, now, so let's talk about solving, talking about solving here. Well, square root of 3 plus I here raised to the power of 10. Right, remember here, using the traditional method, this is impossible, okay? Impossible. Maybe you have to take the whole day into solve it, okay? But using the Moivre theorem, I can finish it in about 5 minutes, believe it or not, okay? So what it says is that, well, instead of representing square root of 3 and I here, so I'm going to represent with, okay, 2, okay, and then cosine 30 degree plus I sine pi 6. I'm sorry, I'm going to say pi 6. Okay. Okay. And then raise to the power 10. Yes. Right. Okay. So I didn't, from here to here, I did not do any change, except that this one here expressed in simple a and b number, but this one I am choosing to represent square root of 3, 1 here in trigonometry. There is no change at all. Nothing changing. Right? And then here, from here, according to the formula from the Moivre theorem here, I can easily say that, well, so this one is the same thing, 2 raised to the power of 10, okay, and then what? And then cosine pi 6 times 10, right, which is this one, right, and then plus I here, sine pi 6 10 here. Did you see it? Okay, so I should be able to finish it in about 5 minutes, okay, instead of the whole day using this one directly using number, right? Okay, well, 2 raised to the power 10 here is going to be cosine. Remember here, this one is 30 degree, am I correct? What is 30 times 10? 300, am I correct? Yes or no? Right, it's very simple. It's going to be equal to 300 degree plus I here sine 300 degree, right? Okay, now, so 2 raised to the power 10. It's very simple. You can just go ahead and use it in your calculator. I think that according to my note, it's 1024. Yes, 1024. So 1024. And then what is cosine 30 degree? Well, cosine 30 degree is this one, right? Okay. So it's going to be on the fourth quadrant here. So this one here is going to be cosine. This one is going to be 30 degree, 300 degree. Am I correct? So it's going to be the same thing as minus 60 degree. Am I correct? Minus 60 degree, right? Yes or no? Right? So cosine 300 degree is going to be the same thing as cosine minus 60 degree. Everybody agree? I'm talking about negative angle, right? Okay. And the same thing here, sine 300 degrees can be the same thing as sine negative 60 degree, right? Right. Okay. And then here, and then let's move on to the next one here. 10,000, 1024, right? Well, cosine of negative 60 degree, because cosine is a even function, so the negative disappear. I got only cosine 60 degree, right? Okay, and then but sine here, sine is actually a odd function, right? So whenever that you give it a negative angle, so the negative going up, negative going up is a minus I here, and then sine 60 degree, right? Okay, and what's next? Well, it's very, very simple here. I mean, you don't have to come to differentiation class in to solve this one. It's going to be 1024. So this one is going to be 1/2. Am I correct? Because cosine 60 degree is 1/2, right? And then here, sine 30 degree is square root of 3 divided by 2. Am I correct? Yes, it's going to be minus here 1/2 square root of 3i. Yes. Okay. And then what is next? Well, the next one is going to be equal to what? It's going to be equal to 512 minus 512 square root of 3i. What is that one? That one is actually exactly this one. Did you see it? How many time I spent into solve from here to here? Less than 5 minutes, right? Makes sense? It's very, very simple. Makes sense? Okay. What is this one? 512 is actually A, and this one is B. Did you see it? Right. Okay. Well, I spent almost 30 minutes in to explain this one here, even though it is not part of the curriculum here, but nevertheless, it is very, very useful. So what I'm trying to say is that, well, if you look at this one here, so the pattern I'm using is this one, okay? So here that I got square root of 3 plus 1i raised to the power 10. So first of all here, I need to convert into, well, into here 2 cosine cosine 30 degree, right? And then plus I here sine 30 degree, right? And then from here I get the result. So meaning here in general term, so I get here A plus BI here to the 10. So it's going to be equal to, and then we have to convert into polar system. Okay, and then go ahead calculate, right? And then after that you get the result, and the result is going to be return it back to A plus B arrow. Did you see it? Right. So in this case, well, the polar system, which is using trigonometric form here, is actually just a stepping stone. Did you see it or not? Stepping stone, right? So I'm going to use it in order to calculate raising the power to the 10. And after I finish, I turn it back into the AB form, right? So this one, what I'm trying to say is that, well, there is such thing as a stepping stone in order to achieve your goal, right? So what does it mean in the context of the Laplace transform? Laplace transform also the same thing. Laplace transform here serving a purpose of just like a power system here. So it is just only a stepping stone in order to calculate. And once you finish the calculation, you can go ahead, return it back into the original form, right? So So in term of Laplace transform is like this here. Sometimes that you have a dE here, right? And then sometimes here that the dE is not possible at all solving it. So we have to convert into what we call Laplace form, okay, and do the calculate, and then go ahead calculate, evaluate. Okay, once you finish evaluate and getting the result, and then return it back into the dE. But so this is just only a stepping stone. Okay, so once we achieve getting the result, and then we get rid of it, and going back all the way here into the dE form. Okay, so it is very, very similar to the polar system. Okay, so polar system here, we use it not simply because we are going to use it permanently, but we are going to just use it only in order to facilitate our calculation. Once we get the result, and then we toss it off, we kick it off. Okay, we're going back all the way here into the AB form. Okay, stepping stone. Okay, so okay, now so the idea of the Laplace transform is like this. Okay, so let's say that if you have a dE here, the dE here. So let's say I'm just making up a number here. Let's say I'm just making up an example here, not necessarily always true. Let's say 3t y double prime plus 2t y single prime plus something 4 y equal to 0 here. So in this case, we are going to change it into instead of this one is t. Am I correct? So I'm going to change it into s. Okay. So what is s? S is actually a variable that is belong to the Laplace transform. Okay, we turn it into s something s here, and then after that you go ahead and evaluate here. After you finish evaluating here, then you get the result, and then turn it back into t. Right. Okay. So this one is just very, very similar into the case of polar system here, which is cosine and sine here. So we're just using this one in order to facilitate our calculation. Once we finish with the calculation, okay, so so after that we get rid of the s and going back all the way here into t, because t is our original form, right? So t, turn it into s, go ahead, calculate, evaluate. After you finish, turn it back into t. Did you see any similarity between the way that I explained the Moivre theorem and this one, right? So t, remember here, this one is actually in t, in terms of t, am I correct? Right? Okay. So go ahead, turn it into s. What is s? S is actually a symbol, a variable that is representing the Laplace form. After we finish with the Laplace form, and then turn it back into t. So this one is no longer exists. This one is just only a stepping stone, right? Okay, so it is exactly what we did in pre-calculus, turning this one into sine and cosine. After you finish calculating, turn it back into AB. That is the way we do it. Okay, now, so first of all here, so let me explain about the definition. How do you turn from T into S here? Okay, there is a definition here, but you do not have to memorize, because it is very, very tedious, and it has a lot of things to do with calculus 2, which is what we call a hands on, not imperfect, improper integral. So we are not going to touch it, but it nevertheless here that you need to understand. Yeah. Well, so let's say if you have a dE here, and the dE here is represented in T here. Okay, right? So this is the dE here. Okay, now and then here we need to turn it into Laplace form, right? The symbol for the Laplace form is like this. Okay, so it's kind of a L here. I think using a script or something L. Okay, so this is a symbol saying that, well, you have a dE, and the E here is always represented in independent variable of T. Am I correct? So we are going to turn it into S. Okay, why S? Because, well, it has been proven that if you turn it into S here, it's very simple to calculate, and after you finish calculation, turn it back into T. Right? Okay, so the formula here, you can write it down here. So it's going to be equal to, okay, integral 0 infinity. Remember here I'm talking about improper integral. Improper integral is always either the lower bound or the upper bound consisting of infinity here. Okay, and then E S T, okay, and then F T D T. Okay, so this is the formula for turning from T into S. Did you see S here? Okay. Well, again here, you do not have to worry too much about this one, because all I need to do is to memorize, and I think it's to memorize 1, 2, I think about 5 or 6 here, formula here, okay? So what is the first one? The first one is this one. So let's say if you have a ft here equal to EAT, right, okay? So this one is exponential function, right? Okay, and then, well, the exponential function here, that the base is E, and then the power is AT. What is A? A is just only any number, right? So if you have to turn this one here into Laplace form here, it's going to be, the symbol is going to be like this. Laplace transform is going to be equal to 1 over S minus A. Did you see it? Right. So this is the first one that you need to memorize. 1 over S minus A. Right. Okay, this is the first one. I just want to make sure that you understand the symbol. Okay, so this is a dE here. Okay, it's consisting of T. So I'm converting here using a Laplace formula, converted into S. That's it. Okay, did you see it? So this one doesn't has any T whatsoever, because that we are trying to convert from T into S. Why we have to convert into S? Because it has been proven that if you are in an S form, it's very simple to calculate. Once you finish with calculation, and then you have to turn it into the original T, so that's Laplace. Okay, so this is the first one. What is the second one? The second one is like this. Okay, so let's say that if you have a dE here in terms of T here, yeah, so I get T to the n, right? So if you have to turn it into S form, Laplace transform is going to be equal to n factorial over S n plus 1. Yeah, this is the second one. So it's look very weird. That's why I said that this is kind of weird science. Weird, very weird, right? And then what is the next one here? Well, the next one here, so I'm going to say that, well, Laplace transform of sine AT, right? So again, we are trying to convert this one here, the function, the dE here, from T into S. So this one here, okay, so this one here, the formula here, remember here, this one here, all about S. The T is no longer exists. So this one here is going to be, well, it's going to be A over, right, S squared plus A squared. Okay. So what is cosine? Well, cosine also the same thing here. Laplace transform of cosine AT, okay, it's going to be equal to S over S squared plus A squared. Okay, if you are curious, how do you get from here to here? Well, again here, that you get from here to here is using this one. But I decided not to cover this one because it's too very too tedious, very tedious, right? Okay, okay. And then what is the next one? The next one here is going to be very similar to the sine and cosine here. So let's say if you have a hyperbolic sine and cosine, do you remember hyperbolic sine and cosine? Hyperbolic sine and cosine here. So if you have sine h, okay, and then at here, okay, Laplace transform of sine h is going to be equal to almost the same thing, but instead of plus, we got minus. So I got a here, sine s squared minus a squared. Remember here we got h here. So this one doesn't have h. This is what we call hyperbolic trigonometry. Okay, now what is the next one? The next one here is going to be, well, cosine h hyperbolic cosine a t here equal to a, excuse me, s squared minus a squared. That's it. Okay, 1, 2, 3, 4, 5, 6. That's it. 6 only. I'm going to give you only the simplify Laplace transform, just only 6. Right. Okay. Now, for your knowledge here, just in case you already forgot, so you have to understand also that, well, here, sine 8 t here equal to sine 8 t here equal to what? Equal to e t minus e negative t divided by 2. Okay. And then cosine 8 t here equal to e t plus e negative t divided by 2. That is what they call hyperbolic sine and cosine. Hyperbolic trig. For those, I think that you should get it here in either calculus 1 and calculus 2. Hyperbolic. Okay. Okay. So those are the 6 form that you need to understand. You need to memorize. Okay. Excellent. Okay, so I'm going to give you a couple of examples, and that's about it. Okay. And again here, for 6.1, I do not have appropriate homework because the textbook is treating this subject very differently, which I don't like here. For that reason here, that for 6.1 here, I'm going to give you a handout. So the handout consists of the problem and also the solution. Okay, so I encourage you, even though that I'm not going to grade you, and encourage you to just go ahead and do it. Okay. But as far as 6.2 is concerned here, well, we do homework. Okay. 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 So let me give you a couple of examples. I'm not so sure we have finished, can finish all of the examples, but nevertheless, I will try. Okay. So let's say if you have a DE here, the DE is very simple. It consists of only one single term because we are learning from the basic. So let's say if you have a dE here, the dE is ft here equal to, okay, what you got here is equal to 2t to the fourth. Okay. So in this case, so you need to turn from t here into s, which is the Laplace form. Okay. So in that case, it's going to be, well, the Laplace of ft is going to be equal to the Laplace of 2 and then t4, right? For curly brace, right? Yes. So in that case here, so whenever you have a constant here, you can take it out. The same thing, just like, so let's say if you have to integral here, so let's say if you got 2t to the fourth dt here, you can take this one out. Am I correct? 2 and then t to the fourth dt. Am I, yes or no? So this is what they call linear. They are being linear, right? For those of you who learn linear algebra, this is what they call linearity. Linear. Okay. And the same thing, so let's say if you have that, if you have to differentiate here, so let's say, well, 4t cubed, 4x cubed, let's say. Okay, so in that case, you can pretty much take this one out. It's going to be equal to 4 and then dx x cubed. So it's going to be equal to 4 and then what? And then it's going to be times 3 and then x second. Am I correct? This is right. The 4 here being constant coefficient, you can take it out. And the same thing here with the Laplace transform here. Whenever you have a constant coefficient, you can take it out. So this one is going to be the same thing as 2. Okay, take this one out, Laplace transform, and then t to the fourth. Did you see it? Right. Okay, everybody okay? What is the rule? The rule is that whenever you have a constant coefficient, you can take it out. Just like the case of integration, just like the case of differentiation, you can take it out. Okay. Now, once you get this one, go ahead and focusing only on this one. This one is actually the same thing as this, right? Yes, this is exactly the formula that we are going to adopt. Okay, so it's going to be equal to what? It's going to be equal to 2, right? Okay, according to this formula here, the n equal to 4, so it's going to be time 4 factorial and then s 4 plus 1, right? Okay, what is 4 factorial? 4 factorial is actually the same thing as 2 times 1 times 2 times 3 times 4 and then s to the fifth, right? And this one becomes 24, and 24 times 2, 24 times 2 is going to be equal to 48 s to the fifth. Did you see it? Right. So what is the difference between this one and this one? This one is expressed in terms of t, and this one here is expressed in terms of s. Right. Why we have to express in terms of s? Because it has been proven that if it is in this form, it's very, very simple to calculate. Sometimes that if you that doing is that if that the situation is not solvable using t, we can easily solve it using s. We'll see. Make sense? Okay. So this is in terms of t, but somehow, just like in the case of the Moivre theorem, the one that I explained just a while ago, we convert into s in order to make it easy to calculate. Once you finish with the calculation, turn it back into t. So that is the whole purpose of Laplace transform. It's a stepping stone. So we are not going to be there permanently. We just want to make an easy calculation. Once you finish, go back into the t. Right. Okay, that is the whole purpose. Okay. Okay, now, and then after that here, so let's talk about another one here. Okay, so this time around here, so I got that the dE here, the dE is very simple. The dE here is going to be 4t minus 10 here, let's say. Right. So how do you convert from t into s? Because I would like to make an easy calculation. Well, again here, all you have to do is just go ahead using the Laplace symbol here. So Laplace here, 4t minus 10 It's going to be equal to, okay, Laplace 4t minus Laplace 10. Am I correct? Yes or no? Right. Okay. And then here, look at this one here. Well, just the way that I explained just a while ago, whenever you see a constant coefficient, you can take it out. It's going to be here 4 Laplace transform of t. Right. Am I correct? Right. Okay. Now, so this one is 10. Am I correct? Yes. Okay. Now, and then here, well, we can pretend here that we got t to the 0. Are they the same or not? T to the 0 is actually equal to 1. Am I correct? But nevertheless, here that we would like to use this one in order to make it easy, in order to fit into one of the formula. Right. Okay. And this one also the same thing. So I consider 10 is actually just a constant coefficient. Take it out, minus 10 Laplace transform t0. Did you see it? Right. Okay. So why we are doing this? Because we would like to convert the t here from t, the dE, from t into s. Why we have to convert into s? Because it has been proven that if it in s, is easy to calculate. Sometimes that a dE cannot be solved using whenever that it is in t, but you can solve it using in s form. Okay. Right. Okay. So it's going to be here 4 and then, well, 1 factorial, because this one here has a power of 1. Of course, 1 factorial is 1, right? And then s 1 plus 1, right? Okay. Now, and then here, what is second term? Second term is 10, right? Am I correct? And then 0 factorial, and then s 0 plus 1. Right. Okay, what is 0 factorial? Remember here, by definition, 0 factorial is 1. Okay, do not confuse saying that, well, 0 factorial is 0. No, 0 factorial is 1. 1. Okay, keep in mind. So this one is actually college algebra. 0 factorial is 1. Do not get confused. Do not say that, well, 0. No. So it's going to be here 4s squared minus 10s. What is this? This is what they call Laplace form. Why we have to turn into Laplace form? Because we would like to have an easy calculation. Yes. This is the original dE, and it's expressed in independent variable of t. Right. Okay. So we convert into s. Why? Because we would like to have an easy calculation. What is this? This is just only a stepping stone. After I finish with the calculation, I'm going to get rid of it. Yes, makes sense a lot, right? So the whole idea is actually exactly the same thing, just like we are converting from B form into cosine and sine. After we finish, going back into AB. Is that make sense? Okay. 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 So this one also the same thing. So let's say if you have a dE, so let's say dE is very simple. dE is in term of t here. So I got here, let's say 10 t to the fifth plus 16 t plus, let's say, well, so this one is the cube. Let's say I'm just making up a number, and then 4 t squared, and then minus, let's say, 5 t here. Okay, and plus 4, let's say. Okay, I can pretend that this one is t to the 0. Correct, right? Okay, and then here, just like the case of integration, just like the case of differentiation, we can do it term by term by term by term by term. Same thing, right? So it's going to be here, it can be equal to, well, Laplace transform of ft. It's going to be equal to, I'm making a shortcut, the 10 here, Laplace transform of t fifth, right, plus 16 Laplace transform of t cube plus 4 Laplace transform of t squared minus 5 Laplace transform of 5 gives me t here. Okay, and then plus 4 Laplace transform of t to the 0. This is yes. Okay, so here this one is going to be 10, right? 5 factorial, and then s 5 plus 1. Right, and the next one here is going to be 16, right? Okay, and then 3 factorial t 3 plus 1. Why? Because it is that is what exactly the formula. How do you get the formula? That you get it from this definition. It's too long. Right. Okay. Now and then the next one here is going to be here 4 and then 2 factorial t 2 plus 1. And then minus 5 and then 1 factorial. Sorry, this one is s. This one is s. This one should be s. This one is s. S, right? 1 plus 1. Right? And then plus here, plus 4, 0 factorial, and then t 0 plus 1. Okay, so what you got? Well, 5 factorial, if I'm not mistaken, is 4 factorial is 24. Am I correct? So 5 factorial is going to be 120. Correct me if I'm wrong. 5 factorial, because 1 times 2 times 3 times 4 times 5. Let's get 120 here. So 10 times 120 and then s to the 6. How do you get 6? 6 is actually 5 plus 1. Right. Okay. And then, well, this one here, 16 times 6. 1, 2, 3, 1. Yes, 6. Okay. 3 factorial is 6 here. And then s to the 4th. And then plus 4 times 2 and then s to the 3rd. Right. And then minus 5 times 1 s second. Okay. And then plus 4 times 1 t to the 1st. That's it. Okay. So this one is in term of independent t, but here it is in term of s. Why we have to turn it into s? Because it's going to facilitate my solving the dE, right? It has been proven that in term of this one here is going to be very, very easy. We'll see. Okay, but for the time being here, well, I would like you to just go ahead and swallow it up here. We are going to talk about the next step maybe tomorrow. Okay, so see you again tomorrow. Okay, so I'm going to give you more example here. Okay, see you. Bye-bye.